Hello everyone, my name is Hyunjun Lee and I'm from Seoul National University. In this talk, I'm going to present NeuroEngine, a hardware-based event-driven simulation system for advanced brain-inspired computing. This work was done with my fellow students and my advisor, Professor Jang-Woo Kim. Let me start with a brief introduction of the brain-inspired computing. Brain-inspired computing mimics the computing mechanism of the brain to understand how the brain operates, and apply them to advance various areas in computer science. The following are some example benefits of the brain-inspired computing. First, it can be applied to recognition tasks such as object detection and classification as in conventional deep neural network. Aside from the recognition task, it opens a broader range of applications and benefits. For example, it can benefit from the extreme low power operation using spikes. Also, by modeling the brain, it can lead to better understanding of the brain. Lastly, it can be applied to model the cognitive function. The potential efficiencies and broader computing capabilities make the brain-inspired computing a powerful emerging computing method. The most common way to model the computing capabilities of the brain is to use spiking neural networks, namely SNNs. SNNs model the computing capabilities of the brain using a directed graph. Each node represents a neuron and the edges represent the synapses. A synapse has a dedicated weight and delay which affects how the neurons behave according to the input spikes. Also, each neuron keeps a time-varying state called voltage, which changes with both incoming spikes and time. Let me introduce the background and motivation of our work. First, I'll explain the most representative SNN simulation methods called the time-driven simulation method. To simulate SNNs, existing simulators adopt a time-driven simulation method. The simulator computes the state change every time quantum of the simulation called time step. There are two main stages for each time step. The first stage is neuron computation stage. In this stage, the simulator updates the internal state of the neurons. The next stage is weight accumulation stage. In this stage, the simulator accumulates the weight of the incoming spikes using the accumulation buffer. In this example, the neuron 1 is connected to the destination neuron with the weight of 5 and delay of 1. Therefore, the simulator accumulates the weight 5 to the buffer for the time step 1. Then, the simulator moves on to the next time step to perform neuron computation and weight accumulation again. The same thing happens at the next time step. In this case, there is an accumulated weight at the previous time step. Therefore, the simulator uses the accumulated weight and the previous state to calculate the next state. And then it performs weight accumulation again. The simulation continues, and in T5, the voltage of the neuron exceeds a predefined threshold. In this case, the neuron fires a spike, and the simulation proceeds. This is the basic mechanism of the time-driven simulation, and as you can see, it incurs excessive number of neuron computations. Then, we profile the simulation latency of the time-driven simulator on 6 representative benchmarks. The result indicates that the neuron computation indeed becomes a critical performance bottleneck by taking 87.5% of the simulation latency. Next, I'll introduce another simulation method to overcome the problem of the existing simulators. To resolve the problem, there is another simulation method called event-driven simulation. The key idea is to perform neuron computation only when there is an event, which indicates that a neuron either receives or fires a spike. Therefore, the simulator keeps an event queue to schedule the events. In the first step, the simulator skips the computation as there is no event. and then it accumulates the weight. After accumulating the weight, the simulator schedules an in event which indicates that a neuron receives a spike. In the next step, the scheduled in event triggers the computation. It updates the state change over 2 steps at once. After the computation, the simulator predicts the next firing time of the neuron based on the current state. Then it schedules an out event which indicates that a neuron fires a spike at the given time step. Next, it performs weight accumulation while skipping the neuron computation as there is no scheduled event, and the events are scheduled in the time order. At T3, the simulator performs a neuron computation due to the scheduled in event. Then it schedules a new out event at T5 after the prediction. Due to the scheduled out event at T5, the simulator performs a neuron computation and the neuron fires a spike. This is the basic mechanism of the event-driven simulation. As you can see, it incurs only 4 neuron computations compared to the 8 in the time-driven counterpart, and thus it reduces the number of neuron computations. To profile how many computations can be skipped using the event-driven method, we profile the number of computations on representative benchmarks. The result shows that the event-driven simulation reduces neuron computation by 8.54 times over the time-driven simulation, and therefore, it is a highly promising solution to design a simulator based on the event-driven method. Motivated by the potential efficiency of the event-driven method, we extend the existing time-driven simulator to support the event-driven simulation. The figure illustrates the basic working mechanism of the event-driven simulator. As the first step, the simulator performs neuron computations. To perform neuron computations, the simulator pops an event. Then it calculates the next state of the neuron using a data path to calculate the state change and predict the next firing time. After that, it stores the updated state to the memory and generates a spike if the voltage exceeds the threshold. Finally, it stores an out event to the event queue. The second step is to perform weight accumulation. The simulator first iterates over the generated spikes at the spike buffer. For each spike, it searches for the destination neurons using the synapse memory, and then it accumulates the weight to the destination neurons. At the same time, it schedules in events to the event queue, and this is the basic working mechanism of the baseline event-driven simulator. However, the baseline event-driven simulator is much slower despite its high potential. Our evaluation using the baseline simulator showed that the event-driven simulator achieves only 0.58 times simulation speed and 0.65 times energy efficiency over the time-driven simulator. Next, I'll introduce 3 key ideas to design a fast and efficient event-driven simulator. First, we identified that the baseline event-driven simulator requires complex computations and incurs high per-computation cost. We propose to simplify the computations to reduce the per-computation cost. Second, we identified that the baseline cannot fully reduce the number of computations due to the invalid events. We identified 2 types of invalid events and removed them from the queue. Lastly, we observed that both neuron computation and weight accumulation require event scheduling and suffer from the resource contention. To solve the problem, we identified the neurons that are not likely to fire a spike and skip event scheduling for the neurons. First, I'll explain how we simplify the computations. From the analysis, we observed that the event-driven simulation requires a complex set of computations to calculate the state change over an arbitrary time interval. If the time interval becomes larger, the simulator may suffer from the precision overflow. Also, it requires a power and area-hungry division-based prediction method to predict the next firing time. First, we reduce the bit precision requirement of the large time interval by splitting them if the precision overflows. Second, we propose an abstract divider which simply replaces the divider into a shift-based logic. Using the two simplification, we reduce the per computation cost. Next, let's move on to removing invalid events. I'll introduce how the event invalidation significantly reduces the number of computations. In the example, the simulator performs neuron computation due to the in-event scheduled at T1, and after the neuron computation, the simulator scheduled an out-event at T6. Then, upon receiving a new incoming spike, the simulator schedules a new in-event. In this case, we remove the pre-scheduled out-event at T6. The reason is that due to the new in-event scheduled at T3, the simulator will predict the next firing time again at T3. Thus, the previously scheduled out-event at T6 will become outdated, and our optimized queue removes the event. Then, the neuron receives another incoming spike at T3. In this case, the simulator can merge the in-event with the pre-scheduled in-event at T3, as it is scheduled at the same time step. As a result, we reduce the number of computations. Compared to the naive queue, which keeps 3 remaining events, our optimized queue keeps only a single event. Lastly, I'll explain how we skip scheduling in some cases and mitigate resource contention. I'll show you how the neuron computation and weight accumulation interacts with the event queue. In the baseline, the simulator schedules an in-event for each weight accumulation. Also, it schedules an out-event after the neuron computation. As both computations require event scheduling, the event queue suffers from the resource contention, and therefore they cannot be parallelized. Our key idea is to defer the computations that do not incur an output spike. In this case, the neuron is not expected to fire a spike after receiving the first in-event. Then, the simulator defers the computation. As the computation is deferred, the simulator does not suffer from the resource contention. The simulator defers the computation until the neuron is expected to fire a spike. After receiving the last in-event, the neuron is expected to fire a spike, and thus the simulator no longer defers the computation, and then it flushes the computation. The event scheduling for the deferred computations can be skipped as they are not expected to fire an output spike. Using the method, we mitigate the resource contention in the event queue. Now, let's move on to how we design our simulation system using the 3 ideas. In the baseline, the simulator suffers from 3 challenges. First, it suffers from the complex computations of the event-driven method. Second, it keeps invalid events inside the queue. Lastly, it suffers from the resource contention in the event queue. NeuroEngine tackles the 3 challenges by adopting the 3 key ideas into its architecture. First, we introduce the optimized data path, which simplifies the event-driven computation, and thus it reduces the energy consumed on the data path. Second, we introduce a composite queue structure which detects and removes invalid events. Lastly, we adopt a lazy update method which defers the computations for the neurons that are not likely to fire a spike, and then it skips the event scheduling for such neurons. Using the method, we remove the resource contention in the event queue. To deploy a spiking neural network on the NeuroEngine hardware, we provide a programming interface. We also design a compilation toolchain to first validate if the network does not violate the hardware constraints. Then, it uses the network parameters to calculate the optimization parameters for event-driven computation. It also maps the neurons to each core in a way that minimizes inter-core connections. Lastly, it loads the data to the NeuroEngine via the hardware interface. Let's move on to the evaluation result. To evaluate the performance, we made RTO designs for NeuroEngine. Then we synthesized the code with 65nm standard cell library. We select the commonly used benchmarks we collect from both neuroscience and computer engineering publications, and please refer to our paper for more detail. We evaluate the effectiveness of our three optimization schemes. First, we evaluate how much energy consumed on the data path can be reduced after our data path optimization scheme. The graph shows the energy consumption normalized to the baseline data path. The result indicates that our data path improves energy efficiency by 1.37 times compared to the naive design. Then, we evaluate how much computations NeuroEngine reduces by detecting and removing invalid events. The graph shows the number of computations normalized to the baseline event-driven method. Using the composite Q, NeuroEngine operates with 4.09 times less neuron computations. Lastly, we evaluate the additional speedup obtained using the lazy update scheme. The graph shows the latency normalized to the baseline without lazy update. The result indicates that NeuroEngine achieves 1.76 times additional speedup with the increased parallelization opportunities. Lastly, we evaluate the overall performance of NeuroEngine over the baseline time-driven simulator. We also compare NeuroEngine against the baseline event-driven simulator with an optimized data path, naive event scheduling, and without lazy update. NeuroEngine achieves 4.3 times speedup over the baseline time-driven simulator. Also, by carefully architecting the data path design and scheduling unit, NeuroEngine achieves 7.4 times speedup. NeuroEngine also shows high energy efficiency improvement. It consumes 2.6 times less energy compared to the time-driven simulator. Also, it is 3.98 times more energy efficient compared to the baseline event-driven simulator. I'd like to conclude by summarizing main points. First, we identify the problems of supporting event-driven SNN simulation. Next, we proposed an optimized hardware-based simulator to effectively solve the identified challenges. Lastly, we added programming interface and compilation toolchain to design an end-to-end event-driven simulation system. Thank you for your attention, and I'm more than happy to answer your questions.